So, the second part, there are some points that I want to mention. First of all, let me address what you said, because you know, in high school, you already know these things. So you might say that, okay, we have a very simple proof for this. Why we suffer so much to prove this? Because in high school you learn that. Of course, we will learn today, but let us assume that you know that. So what do you do, for example, if you want to calculate this? According to what you learned in high school, you find the primitive function for this, which is capital F, and then replace x there, replace 8 there, and subtract it. And of course, this is nothing except my area function. And now, instead of going so long path, I can just differentiate both sides. The derivative of this one becomes a prime of x. This becomes the derivative of f of x, and this is a constant minus 0. But then you say that, okay, the primitive function, the derivative of the primitive function is just little x, and you think that this is the proof, yes?
Why are we integrating for x and not t?
Not t. Thank you. Yes. But this is, I just want you to know, because this is not the proof. Yes? This theorem, as we will see, will be proven using the first fundamental theorem. But most of the time, which is the famous one, is the second fundamental theorem. So if someone finds another proof for the second fundamental theorem that will not go past through the first one, then you are right. But the logic is the other way around. We have to, you see that in this proof, I am using the first one. So I have to prove it independently. Yes? Another thing that I want to mention, it is extremely important, is that differentiation is always more or less possible. If I given you a function, even though the function is complicated, you can differentiate it. But this is not the case for primitive functions. For example, if I ask you, can you calculate this? You know that this integral sign is connected to this topic. This is why we are using the same integral sign. But this is called antiderivative. Antiderivative of this one we learned before. What is that? A function whose derivative is e to the x is simply e to the x, or of course plus a constant c. But I just want you to know, this is a mathematical theorem. If I change x to x squared, there is dead end. What does it mean there is dead end? It is not correct to say that there is no function whose derivative is e to the x squared. But the correct way is that mathematician has shown that among the functions which are famous for us, polynomials, trigonometric, logarithmic, exponential, you cannot find any combination whose derivative turns out to be e to power x squared. Yes, do you understand that? So if that is why I want you to understand, this is not always possible to write any integral and say find it. Yes? But if I ask you, can you manufacture a function whose derivative is e to power x squared? You can. Can you do it now? It doesn't mean that the function that you are telling me is in terms of logarithmic, exponential, polynomial, and famous functions. But that is a function. Being a function, you shouldn't be famous to be a function, it's a function. Okay? So which function, can you artifact a function whose is the primitive function of this one? In other words, its derivative is e to power x squared.
E by 3 to the power of x cubed?
No, it doesn't work. I just told you, believe me. Mathematicians have proven that this is impossible. Don't look among the normal functions. There is no combination of the functions you know so that its derivative miraculously cancels out and gives you this. Now trust me on that. But still, I am asking you, can you give me a function, not a famous one, but manufacture a function right now, whose derivative is e to power x squared? And use fundamental theorem of calculus, just we learned. If you didn't know that, there is no way to do it. The function is this. I write integral. I want you to feel, because you might think that I am cheating. Okay, it's not if you understand I am not cheating, it means that you understood the fundamental theorem calculus very well. Okay, the function is this. E to power t squared dt from 0 to x.
Yeah.
This is your function. Is this a function of x or not?
Yeah.
Yes. And what we learned just now is the derivative of this one is, according to fundamental theorem of calculus, what is the derivative of this one? Instead of t, you put x. So this is your function. This is a function whose derivative is e to power x squared. Okay, but this function, you might say, oh, this is not a good function. No, it is not a famous function. I agree with you, but that's a function. And its derivative, according to fundamental theorem of calculus, is this function. Okay? Is that understandable or not? If you don't feel it yet, if you still believe that I am cheating, it means that you didn't learn it very good. If you go home and think about it, probably you will understand it. Okay, so this is a function because I didn't ask you to give me a famous function because mathematicians have already shown that it is impossible. Okay, when they prove something is impossible, it is impossible forever unless they change the axioms. Okay, that's the good thing about mathematics. It's not physics or philosophy that changes. Yes. So this is a function whose derivative is equal to this one. Yes, please.
Does this imply that it is that derivative on that interval specifically, or is it on the entire EX squared?
Yes, that's a good subtle thing, because if you have read my definition, yes, you can say that this is, but by the way, I can relax that condition. I can say that because this is continuous everywhere, so if x is any number, this function exists and its derivative is that.
Right, so if you just put x as infinity, then it goes to the same...
No, infinity, no, if you put infinity, it is not a function. It is a constant function, it gives you a number and its derivative is 0. Of course, if I put infinity here, this integral will diverge. But if I put a minus sign and I put an infinity here, that integral converges. But it becomes a number. At most, what you can say is a constant function. And you know that the constant function derivative is 0, it is not my function. Yes? So, do you understand? The whole point is that the upper limit is not fixed, it's a variable. By changing that variable, I am changing the value of the integral. So this means that this integral depends on this variable. When it depends on it, it means it is a function of it. Yes, we can discuss after the lesson, okay? Because there are many things we have to consider. But I just want you to know, because this is very common. Students write integrals and give them to the teachers. Okay, solve this integral. Okay, there is a competition in MIT. People actually compete. Two groups, they compute. They give one integral to the other one, and then the other group give. Then they see which one is going to do faster. But those integrals are hard to do, but it is doable. But it doesn't matter how genius you are, this integral, if you are looking for famous function, mathematicians have shown that this is impossible. Okay? But we immediately manufactured that function for you. Yes? But still you believe, oh, what is this function? Because you have used to normal functions. Yes? By the way, if this is e to the power of minus t squared, this is in statistics, that is called error function up to a constant. Yes? So that's an error function. Error function is defined in terms of an integral. Yes? For example, you might say that, okay, I know ln of x. But ln of x, if you see the book, it is defined based on an integral. It is the integral of this function going from 1 to x. But because you are familiar with ln of x, you feel you know ln of x. No, someone has talked about this. So every property of ln can be deduced from this formula and the formulas of integral. Yes? Okay. If it is a little bit confusing, we can discuss after the lesson, because I have to continue with all the things that is left. Okay, these are very important formulas that you see on the slides. So let me show you. This is just a fundamental theorem of calculus. I want you to understand it. If I have an integral, f of t d of t, the lower limit is a constant, the upper limit is x, only x. If I want to differentiate it with respect to t, for example, can I talk about differentiation with respect to t? Yes? It's a very different thing. I want you to feel, because this expression that you have here is not a function of t. Yes? At the end, it will be a function of x, and I am differentiating it with respect to x. This is the standard one. Usually you don't need to do anything except replacing t with x. Yes? Understandable or not? Okay. But this is useless. I mean, this is not very interesting. It's not very rich. What happens if I have the same structure of the integrand f of t dt? It goes from a, but not to x, to a function of x squared plus 5, or something like that. Should I stop, or can I find some way to do it? The answer is no, you don't need to stop. This is the new formula for you. I want to derive it for you because it's important to understand. So you see, this is integral from a constant to x only f of t dt. You want to differentiate it with respect to this x. The answer is simple. Replace x, t with x. Yes? Yeah? This is what we proved actually by intermediate value theorem and things like that. But now the question is that, what should I do with this? If this is not x, it is a function of x. My claim is you can prove it like this. You can write it as, you can replace t with g again as before, but it is not enough. You have to multiply by the derivative of the upper limit as well. Is that clear? So forget about the concept now, because if you are still thinking about what is happening there, it will not allow you to learn this one. This is a technical one, so this is not hard to learn. This is the fundamental one. If this is x, this is a constant, I just replace t with x. What happens if I have a g of x? I still replace t with g of x, but that is not the end of the story. You have to multiply it by g prime of x. I want to prove it for you because it's very simple. How can I prove it? So let us write a of x to be integral from a to x f of t dt. This is something you already know. If I ask you what's the derivative, you immediately answer. But can you tell me what is the integral, and let me call this one a function of x. So let me not make it complicated. So integral of a g of x f of t dt. Do you see a connection between this function that I am interested in calculating its derivative and the area function? Do you see a connection? How can I use this to construct this function? For example, if I ask you what is a of 5, you immediately answer. What is a of 5? Integral from a to 5. What is a of 7? Integral from a to 7. So what is a of g of x? Very good. This is nothing except a of g of x. This new function is a after g. So it is the chain rule. And if I want to differentiate this, integral from a to g of x f of t dt, I can differentiate this one. Yes? So this is my question mark. But I can do this because I learned differentiation rules for the chain rule of the derivative. So what was the formula? Do you remember? It was the derivative of the outer function calculated at the inner function, but I have to multiply it by the derivative of the inner function. Yes? Do you remember that? Do you remember what was the meaning of this notation? This means that the derivative is calculated at the point g of x. Okay? So, if you tell me how can I write this, I have to go back to my function, calculate a prime first, which the first fundamental theorem allows me to do. Yes? And then here, I go there, I replace x with g of x. So this becomes f of g of x multiplied by g prime of x. And that's exactly the formula that I have written for you. So this is a combination of the first fundamental theorem of calculus and the chain rule of differentiation that we learned before. If we combine them together, we will find a formula for the derivative of this type of integrals. Confused or not? Understandable? Okay. But the question is that what happens if the lower one is not constant? If the lower one is also another function, in other words, it goes from h of x to g of x and then f of t dt. I want you to think about it yourself. I will tell you how to do it, but how should I do it? You replace t with the upper limit, but you have to multiply by the derivative of the upper limit. You replace t with the lower limit. You have to multiply it by the derivative of the lower limit, but subtract it. Okay? Can you see why? How, if you want to prove it, how do you prove it? Split it into two. For example, you can write this as h of x to some appropriate number, a, but you go from a to g of x. Yes? The derivative of this one you already know. This is this one. But why the negative sign comes in? Because I have a plus here. Why do you think the formula is minus? Is it a mistake or what is it? We have to flip, not we can. You know why? Because the fundamental theorem calculus is only for the case that the lower one is constant, the upper one is x. But in this case, the lower one is variable, the upper one is constant. It means I have to, if I want to use this theorem, I have to make everything consistent. So I go one step forward. If you don't mind, I will write the positive one here, and then minus, flip them. And now, this is exactly the same theorem I proved, one for the case of G, one for the case of H. So that's the formula. Is that right? Mm-hmm. Okay. So that is the content of this remark. So let us solve one of these exercises. Or we can solve both of them because it doesn't take that much time. So this exercise, in each case, determine f prime of x. F of x is given like this. Okay, so let me do them quickly. They are simple. So f of x is given to be integral from 0 up to what? 2x minus, sine x, 1 minus 3t squared dt. I want to calculate f prime of x. So how should I do that?
Can you change sign with?
Is it the standard? I mean, is it the fundamental theorem of calculus? Not exactly, because I have a function of x up there, even though this is a constant. So this is this new version, this one, only with one function involved. In the future, there are two ways to do it, because in the future you can calculate this integral. You find the primitive function for this and use the second fundamental theorem, find your function, and when you have a function without integral sign, you know how to do it. But sometimes it is impossible. That is the importance of this theorem. Sometimes, as I told you before, it is impossible to find a primitive function, but it is possible to take the derivative of that function we don't have any clue about it. So if I want to differentiate here, what do you think I will do? Help me. Which version is that? This is the version here. Yes, a to g of x. A in this problem is a constant 0 and sine x is up there. And then what should I write? What I need to do is just simply replace t with this function above. It was very simple. But it is not enough. I have to multiply by the derivative, the upper limit. And then you continue until there is no prime left. So it becomes 1 minus 3 sine x squared. And then cosine x. That's it. If it were the other way around, if 0 was up there, sine was below, I have to switch. Because if I want to use these, I have to make sure that I switch or use this version. This version always works, independent of which one is constant, because there is no constant. Is that understandable? So the next function is f of x equal to integral from e to power minus dt minus t squared dt goes from x squared to x cubed. So if this is given, and even if you are good in integration, there is no way for you to do it unless you use the fundamental theorem of calculus, because there is no way we can calculate this integral in terms of the functions we know. But if the goal is to calculate the derivative, we can. We don't even need to calculate the integral. This version is this complicated version, but that's easy. What should I do? I replace this t with the upper limit, So it becomes e to power minus x to power 3 to power 2. But I have to multiply by the derivative of the upper limit. So let me write it in the future if you want to read your notes. And then minus, I do the same thing with x squared. So it becomes e to the power of minus x squared to power 2, but multiplied by x2 prime. Yes? And then you have to continue. So this becomes equal to this one to power 2, e to power minus x to power 6 multiplied by 3x squared. And then here I have minus e to power minus x to the 4th multiplied by 2x. That's it. That's your derivative. Understandable? Okay. If you don't mind, let me skip these exercises a little bit so we can have time, and if I have time we come back to it. So okay, this is a good problem. Let us do that. Example number 3. This is also a good exercise, but if you don't mind, let me skip from it for the time being. And this is an exam question related to this topic. But this one also sometimes people ask you about calculating limits involving integrals in exam. So let us do this example number 3. And I want to wait for you because I'm going very fast. Sorry for that. I know this is stressful for everyone, but this is what we have to do. So I don't know how could I finish even if we didn't have that extra lesson. I don't know. So the limit integral from 0 to x, and I have 2 to power t minus 2 to power sine t dt divided by x squared. X goes to 0 from the right side. Okay, so you want to calculate this limit. How do you think about the problem?
Since it's a 0 over 0 type.
Yes, that is important. Every time you want to calculate the limit, you have to know what type of limit you are facing. The first thing you do, you replace x with 0 to see roughly what is happening. The denominator becomes infinitesimally small. And then if x is very close to 0, this function is continuous. It is proven that if I put 0 here, do you remember 0 to 0? From a to a, the integral is 0. So this is of the type 0 over 0. So it means that I can use Hobbital's rule. Yes? So I differentiate. So instead of calculating this rule, this is Hobbital rule number 1. I'm a little bit sloppy. I am just putting it as if the limit exists. In principle, you have to calculate them and go backward. But let us be a little bit sloppy here to save some time. So I differentiate the numerator and denominator, do you remember, separately. The derivative of the denominator is 2x. The derivative of the numerator is this topic, because I want to integrate a function involving the integral sign. Yes? So what happens here? This is exactly the fundamental theorem, because this is a constant, that is just x. So what I need to do is just replace t's with x. So this becomes 2 to power x minus 2 to power sine x. But what type of limit is this one?
0.
Again 0 over 0. So I have to use Hobbital's rule one more, yes? So this becomes Hobbital's number 1, because there are 2 Hobbital rules, do you remember? So I take another derivative with the hope that finally this will give rise to the answer. So this is 2. And then you have to remember about the formula of derivative of exponential functions. Do you remember? A to power u prime was a to power u multiplied by ln of a multiplied by u prime. That was the formula for this one. So I will write it like this. So it becomes 2 to power u, which is x, multiplied by ln of 2, multiplied by the derivative of x, which is 1. Minus the same story here, 2 to power sine x, and then multiplied by ln of 2, sorry for that mess, and then multiplied by the derivative of sine, which is? Cosine x. Okay, it is very bad. Let me rewrite it here for you again. So this is the 2 to power x, ln of 2, minus 2 to power sine x, ln of 2, cosine x. Yes? And then divided by 2. Yes, that's correct. And then I take the limit, x goes to 0 from the right hand side. I don't have any problems because already I know the denominator is 2, so I'm not in any trouble. So if I put 0 here, 1 ln of 2, so this becomes ln of 2, 2 to power 0 is 1, cosine of 0 is 1, so ln of 2, is that right? Or I missed something? I didn't expect it to become 0. But it is, yes. Am I missing something? No. Ah, yes, I am missing. No, that's correct. Because if I put 0, 2 to power 0 is 1, so ln 2. 2 to power sine of 0 is also 1, so it's 1. Sine of 0 is 0, 2 power 0 is 1. Ln of 2, cosine of 0 is also 1, so that's 0. Hopefully I haven't done any mistakes, I don't know. Yes, but the questions you already had with derivatives, you can also have, but integrals involved now. For example, with the previous question, do you see what the question, I just show you the question. So what is this question? Consider the following function. Hopefully this is not mysterious for you anymore if you see something like this. You know it's a function. And then they are asking you find the maximum and minimum of this function. Yes? So you have to apply the rules for maximum and minimum you already learned. It goes through derivatives. But this time, because the function is defined in terms of an integral, it means that you have to use the fundamental theorem of calculus to differentiate. Yes?
Since our upper bound is a quadratic and sometimes it dips below 0, do we need to like flip it in some cases?
No, it is not important, by the way. No. So don't get confused. You don't need to be worried about if the upper limit is positive or negative. You don't care. As far as it's a function, but what you care is that your constant should be down there. Yes?
That's all we care about. Okay.
Yes, that's what we care. But everything will be taken care of by theorem itself.
Okay.
Yes. Okay, so now, if you don't mind, let me skip a little bit. I will come back to it if we have time. Finally, what you are waiting for, and the reason this theorem is important, you see that so far I want you to feel this is the first time the notion of integral is connected to derivative. Yes? But now the second theorem actually finishes the problem. The problem is this. If the function f, it's extremely important, is continuous on a and b, otherwise you're not allowed to use this. Okay? The claim is that if you want to calculate this integral from a to b, f of x dx, I want you to, if you review, so far there is no way for us to calculate this except that stupid way of Riemann sums and things like that. This is the first time Newton's genius actually provides us with a real way, practical way of doing it. He tells you, if you want to find that unique number that is generated by all those Riemann sums, you can do this alternative way. Think about a function whose derivative is f, which you denoted by capital F, and then calculate this number at the top and the bottom and subtract them. That will be the number that those Riemann sums are going to produce for you. Okay? So this means that I would write it as f x, and this is, by the way, this is the evaluation symbol. They put a vertical line here. Whenever you see this symbol, it means put the upper limit there, put the lower limit there, and subtract them. Yes? So, what is f? F is I emphasize, it doesn't matter which one, a primitive function. Of f. Yes? But because I want to prove it for you, this is the way people write, because we are used to work with x. But let me prove it for you. So I want to change a with, so t, okay? In the proof, I don't want you to get confused between different notations, because in the first fundamental theorem, I use t as the integration variable. So let us stick to the same idea, okay? I want to show that this is fb minus f of a. Yes?
When you say A primitive function. A is a variable or is a letter there?
It is an article.
Okay.
Indefinite article. So it means
Okay.
that there are infinitely many
Yeah,
primitive
yeah.
functions. It doesn't matter because.
Okay.
Look, it is any.
Yeah.
Any primitive.
Okay. So okay. Thank you
Yeah.
very much for correcting. Any primitive function. Yes. Yes. Any primitive function. Okay. Yes. And now, if I want to prove it, how should I prove it? I would do like this. I will consider the area function. The area function is integral from a to x f of t dt. Do you agree? This is my area function. If I ask you what is the derivative of the area function, can you answer that? Hopefully yes. The answer is f of t. Oh, sorry, f of x. Okay. And now answer another question. Remember, f is any primitive function. So let me ask you one more question. What do you think about this? A primitive function, I am saying that f is any primitive function. What is the meaning of primitive function? When you differentiate it, it gives you f. So now there is something interesting going on. I have one function. By first fundamental theorem, I know its derivative is f of x. And now I am telling you f is any primitive function. It means its derivative is also f of x. What does it mean? It means the derivative of two functions is the same function. So what does it mean? According to what we learned before, they are either equal or they at most differ by an additive constant. So this means that, it means that a prime of x is equal to f prime of x. So this means that there exists a c constant such that, for example, a of x, f of x is equal to a, it doesn't matter in which way, of course, this. Is that right? Mm-hmm. But the problem is that I want to have a control over c. This is a constant, but I don't know anything about. But I can get some information about that constant by calculating this at some particular value. I will choose x to be a. Then it becomes f of a equals to a of a plus c. Yes? But this one I don't know because no one tells me what function f is. I know something about area function. Can you tell me what is a calculated at a? From a to a.
No.
It becomes 0. So this one I know. Okay? So it means that I don't know f, I don't know c. But I know this c is nothing except f at a. This I know. Is that right? So, if I put it back here, then I will have f of x is equal to a of x plus f of a. Mm-hmm. Yes? And then I move f of a to the other side. So then it becomes f of x minus f of a is equal to a of x. Do you agree? This relation is valid for every x, including b. So now if I put x equals to b, this means f of b minus f of a is equal to a of b. Yes? Mm-hmm. But what is a of b? A of b means instead of x you have b. So it becomes integral from a to b, f of t dt. So this is nothing except integral from a to b, f of t dt. So this means that this one is equal to that. Okay, so I want you to see how convoluted sometimes it is important to see that the things we learned from limits and then went to derivatives, we were actually making everything on a correct place so that we can come up with this very fundamental theorem finally. Okay, so now calculating this integral is more or less calculating a primitive function because the rest of it is easy. So if I want to calculate an integral from now on, if the function is continuous there, it's extremely important. If it's not continuous, we have some troubles. For example, some people can calculate this integral. So for example, am I allowed to use second fundamental theorem for this integral? No, because the function involved is not defined on this interval. I have trouble with this function at 0. But if you naively use it, you get an answer For example, can you give me a primitive function for 1 over x squared? It's famous. Minus 1 over x. The derivative of this one. And then if you calculate it from minus 1 to 1, what does it mean? It means replace x with the upper limit, replace x with the lower limit, and subtract the one above, so the one below from the one above. So it's minus 1 minus 1. The one above minus the one below. What do you get?
Minus 2.
But it is clear it is a wrong answer. Why?
It goes up infinite.
Yeah, because 1 over x squared is positive. And if you do a Riemann sum, the Riemann sums are all positive. So there is no way that the limit goes to negative value minus 2. So it is extremely important. If you don't have continuity, you are not allowed to use this theorem. If it works, it is a coincidence. But I want you to know, continuity is important. So it is wrong. Yes? So, but if the function is continuous, I hope that you agree with me that the subtle thing is not doing the new thing, putting numbers in subtracting. The subtle thing is what we trained ourselves by doing a lot of primitive functions. So that is why, if you really want to use this theorem, your main problem is to be good in finding primitive functions, because the rest of it would be just a matter of putting numbers and subtract. Is that right? Okay. So now, do you think we should solve this problem?
Sure.
Yeah, I mean, it's very simple, but let us do it once. I want to make sure that you understand everything. So integral from minus 2 to 3, and I have 2x squared plus x minus 1 dx. Okay, so what do you do? First, sometimes you remember, you want to find a primitive function for this. By the way, why a primitive function, any primitive function is enough?
Because when you subtract them, the constant.
Yeah, because other primitive functions, they differ by a constant. If you choose another constant, this constant will appear in fb, and it will also appear in f of a. So they will be cancelled. So it is better not to worry about this constant at all. So if I want to find a primitive function, I would ask myself, what is a primitive function for this one? It is x3 divided by 3, so it becomes 2x3 divided by 3. A primitive function for this is x squared over 2. A primitive function for this is minus x. But then I have to put this vertical line in front, minus 2 to 3. Don't put the integral sign, be careful. It is up to you. I will usually separate it. I replace every x with the upper limit and calculate that. So it becomes 27, 9, 18. And then this becomes 9 over 2 minus 3. So this is 15, 39 over 2. And then I put minus 2 there. So it is minus 16 over 3. And this is 4 divided by 2 is 2. And then plus 2. So it is 412 minus 4 over 3, yes? And then I subtract them. So it becomes the number above minus the number below, whatever it is. So it becomes minus minus. So it becomes plus. Yes? So 90, 107, 8, 115 over 6, yes? So you get a number, whatever it is.
So isn't it 117 plus 5?
This is 90, 27, 117.
Plus 4 is 119.
Yes. Yes. No, plus 8, 123.
Okay, we're going.
Yes.
That was just the
No. This is, yes, this is positive, positive, yes? So this is 90, 27, 117, 8, yes. So 125. Okay, whatever that is. I don't want to waste the time. I am in the stress of time. But do you understand that? The whole point is to find a primitive function. Putting these numbers is sometimes problematic, but it is not hard in principle. Any questions? Okay, so there is something that I want to know, and that is about, this is important to know, because this theorem I mentioned, it works only for continuous functions, but it is a particular case of discontinuity is allowed, and that is the idea of piecewise continuous functions. Okay? So what do I mean by a piecewise continuous function? If I have this function, This is a piecewise continuous function. For example, if this is A, this is B. For example, if this is C, then I can come from here up to there, and then I jump here one single point. For example, I'm just exaggerating, okay? And then I can have this one, and I go here. This is a piecewise continuous function, yes? So it means that it is continuous on this piece, and it's also continuous on this piece. But in total, is this function continuous? No. Of course not. It is defined, the integral of these functions are also defined to be the sum of the integrals on these intervals separately. So that's the definition. So this means that, you see, the whole graph is the graph of one function, which is defined from A to B, but this one is following the same rule, but because the domain is changed, I call it F capital. Let me not call it capital F1. The reason I did it because the book did it, but let me call it G1. G1 means the function restricted to this domain. The rules are the same here, but the domains are different, so in principle I have to change the name of my function, and G2 here. So if I want to calculate integral of f dx from A to B, it is defined semicolon equals to integral of G1 from A to C, and then plus integral from C to B G2 dx. So the only discontinuity which is allowed is this type. Okay? Piecewise continuous. Piece by piece. But on each piece the function is continuous. Okay. I think this is doable. So we have to prioritize because many things are left. There are many exam questions. Not many topics are left. Yes. Yeah.
When we have, I don't know, stocks,
Yes.
we just jump from one value to another.
Mhm.
So it's all kind of piecewise. We can calculate the volume of the stocks using this kind of thing.
No, the
Because
volume means volume rotation.
Yeah, like the kind of the area below.
Yeah, because for that one single point there is no volume
So it
generated.
just fluctuates, so
Yeah,
it's fine. It
yeah,
doesn't need to be
yeah.
piecewise.
Even for the area. So if I ask you what is the area, you can say this area plus that area. What happens exactly at one single point doesn't change the area. Okay, so let me ask you one question. For example, if you see on the notes, I have to skip some of these exercises. But for example here, if I want you to calculate this integral, do you see what the answer is? Yes, why?
It's a null function.
This is one of those integrals that is really doable. So if you see this in the exam, from minus pi to pi, it is one of those integrals that is doable. What does it mean? It means you can find a primitive function for it, and then replace it with pi and minus pi and subtract it. Just to refresh your memory, how do you find a primitive function for this? Do you have any idea?
By parts.
Integration by parts. So it is lengthy. So you have to do integration by parts according to what you learned before, and when you arrive at the final answer, you replace that x with pi, you replace the x with minus pi, you get two numbers and you subtract them. But if, what I told you before, if the interval is symmetric, before even starting your calculation, remember this remark. That might be the designer has used this fact that this is even or odd, so that it makes it a little bit simpler. For example, what type of function is this? Odd, because if you change x to minus x, this will pick up a minus sign, but cosine of minus x is cosine. So overall, I have a minus sign. So this integrand is odd. So the calculation is not necessary. But it is a good practice. Go home and do it in the normal way. Calculate the primitive function, put the numbers and subtract. Okay? So, yeah, so let me skip the things. So this is also good, by the way. So sometimes the integral are not possible to calculate. We are not able to calculate the integrals, but we want to estimate the integral. Yes, I might be able to talk about this a little bit later. But there are some workshop problems, and I don't know if you get any seminar question from that, so let me talk about it. For example, in this example, I want to show that this integral from, where is it? From 0 to 1, x cosine x over x squared plus 1 dx is less than 1/2. Okay? So this is one of those cases, if you can manage to calculate this integral, it becomes a number, and then you see that yes, that number is between 0 and 1/2. But usually for these kinds of questions, they give you a type of integral that is even sometimes impossible to calculate directly or hard to do. So it means that you have to estimate the value. For example, in this case, this estimation is definitely very simple to understand. Why do you think that this integral is definitely positive? Because you know that integrals sometimes are positive, sometimes are negative. But this one is claiming that this integral is always non-negative. Why is that? Because the integrand is positive on this interval. Yes? X is positive on this interval. X squared is positive everywhere, so it is positive, this part. Why cosine is positive?
It's positive from 0 to pi by 2, please.
Yes, because in the first quadrant, the cosine is positive. It is 0 to pi over 2. Pi over 2 is approximately 3.14 divided by 2. So it is bigger than 1.5. So 1 is somewhere here. So if I have an angle between 0 and 1, I am guaranteed to be in the first quadrant. Cosine is positive, this is a positive. So this means that my function is definitely positive. Yes? But I want to fine-tune it so that it gives me a nice upper bound to be 1/2. This is not easy. These questions are very tricky sometimes. But for example, let me write something and see if you believe me or not. Do you agree that this is smaller than x?
Yeah.
Yes? Because x squared plus 1 is definitely larger than 1. Cosine x is smaller than 1. And I am dividing a number smaller than 1 by a number bigger than 1. So what happens for this part is definitely less than 1. And x is positive, and it is multiplied by 1, so it is less than x. But why this is good? Because the integral, so according to the theorem we had, the integral of this one from 0 to 1 is less than or equal to the integral of this one from 0 to 1 is definitely less than integral of this one. That was a theorem, do you remember? From 0 to 1. But what is the answer to this one? 0. This is your integral that you are looking for. Let me call it I. And this integral is easy to calculate. What is the answer? I need to find the primitive function, which is x squared divided by 2, but I have to run it from 0 to 1. I put 1, it becomes 1/2. I put 0, it becomes 0. So subtract them, it becomes 1/2. So I really hate these questions. You know why? Because the person who designed the question is easy because they can think about the questions, but I have a lot of trouble. I mean, because when you design the question, it is easier. You know what the goal is. But how should I know keep x? You know, by practice. I mean, if I hate it, definitely you will also hate it, you know. Okay, so let me at least start one thing. These are the hardest ones. The reason why I'm saying I hate it. We will talk about a little bit of these things in the next module. It's really annoying module next time, okay? It's short, but the questions can be hard sometimes.
Can't I just find the maximum and with the upper bound? Always.
Yes, but what I'm saying is that, for example, if you really want to do upper bound systematically, then you have to differentiate and see what happens. I mean, you lose a lot of time, and then they can make the integrand even harder. Yeah, so that's what I'm saying, but you are technically right. If you can somehow find the upper bound and the lower bound according to the systematic way we learned before, you are done. But at least I want you to see something. Okay, and the 5 minutes we are left, I don't know if you have a little bit more time or not, but the next thing that I want to talk about is the substitution, but in definite integrals. Okay, so if you have this function, it is something like u substitution for definite integrals. In principle, you don't need it at all. Okay? For example, let me give you an example. If I give you this integral, 2x here, x squared here plus 1 to the power of 100 dx. In principle, you should be able to do it by u substitution. Do you agree? Because what you do, you take this u prime becomes 2x dx, and you can do it. Now imagine I give you this. Can you still do it? Yes, because you take this one and use u substitution, you find in terms of u, switch back to x, you have your primitive function, then you put them in. So in principle, substitution in definite integrals for calculation is not that necessary, but from theoretical point of view, it's good to know it. Okay? So let me explain exactly what I want to do here. So if I want to do here, imagine that 0 to 1 is not there. What do? You do u substitution. So you say that u is equal to x squared plus 1, and the rest comes automatically. Do you remember what was it? We take du is equal to the derivative dx. And I have to write everything in terms of u. Be careful. Okay, but if I want to do, I have some problems with 0 to 1. I have to change probably these limits according to new variable. And that's also simple. I would say that x goes from 0 to 1. This implies u goes from where to where? If x is 0, my u becomes 1. If x is 1, my u becomes 1 plus 1, 2. If you don't do this step, you have to switch back to x and then put 0 and 1 there. But if you do this step, you don't need to switch back to x, you can use the new limits. So this means that my integral will be equal to integral, instead of 0 to 1, I write 1 to 2. 2x times dx is nothing except du. And then x squared plus 1 is u, so u to power 100. And then I calculate this. It is u to power 101 divided by 101. But because I already took care of these, I don't need to switch back to x. I put 1 and 2. And then of course it is not possible to, let me just write it down. So it becomes 2 to power 101 divided by 101 minus 1 over 101. That's it. But if I didn't use this theorem, here I will have u, I have to switch back to x and then use the old limits. There are many subtleties coming in, you have to be very careful. I have written this extensively in the notes, please study them, that's part of what you are supposed to do. And I will probably try to make some videos on weekend, I don't know, because I have to prepare the new lecture notes as well. If I have time, I will solve some of them. And some of them I have already solved. There are some videos under the title of Refresh Course. So I have solved many of them on the board. And I have solved some of them on my YouTube channel. So I put the links onto the exam questions. It's better to know them. But most questions are coming from this part. So you have to be very good in it. Yes?
Yeah. In that very last example we had, let's say it was the bounds were from -1 to 1.
Mm-hmm. That's exactly, if you read my notes, then you will get 0.
Yeah, and that's not always true.
No, it's not always true. And that's the subtlety that I have written in notes in extensive way.
Okay.
Yes, you can read that.
Okay, cool.
Yeah, because, and by the way, the exam that do you remember we solved one example yesterday, I thought that there is a plus minus absolute value. When I checked the examiner, he also missed, or she also missed that plus or minus sign. So which is, so that is not technically correct. So you have to take care of absolute value. And then you have to discuss positiveness and or negativeness. But the interesting thing is that the answer at the end in both cases becomes positive. So the answer is correct. But in the middle of the way, you have to consider positive. When it is positive, everything inside will be positive. But when there is a negative, there will be 2 negatives, one coming in. They will be multiplied to positive again. So even if you don't care, but that is not the correct way of caring about it, because you have to put absolute value. There is no exception in mathematics. If a square root of x squared is absolute value of x, it is absolute value of x for eternity. So there is no exception for that. Okay, but I don't know. Might be you do your seminar exam. So that is up to you to read 2 or 3 examples that I missed, and then you do the seminar exam. But might be the next module I have time to complete some of these, because there are still many important things that I didn't do. Because the next module, if I am right, is shorter. It's not that harder. Maybe we can compact it in 2 lessons, probably 1 lesson is enough. Okay, any questions? Thank you very much.
Thank you.